Thank you.
All right, everyone. It's 4 minutes after 2, so I think it's a good moment to get started. I'm Derek Groen, and I'm a lecturer in computer science at Brunel University London, and of course also one of the partners in the Hidalgo project. Today we'll be providing a virtual FabSim3 and MUSCLE3 workshop. FabSim3 is an automation toolkit that allows also file-based coupling, and MUSCLE3 is a dedicated coupling environment. And let's see, the purpose, sorry, there's something happening with my Zoom. Let's see what happens. I will share my screen so that you can see the slides. So let me do that. Can you all hear me well, by the way?
Yes, Derek, we can hear you.
Okay, very good. So the goal of the workshop today is basically to familiarize you hands-on with both the FabSim3 automation toolkit and the MUSCLE3 coupling environment. And basically the workshop in total will encompass 3 hours, but a lot of it will be very hands-on. Well, you have the opportunity to get various things installed and working and try out a couple of applications. But we will also provide a few lectures so that you get a general idea about what these tools are about. First of all, I'll provide a little bit of a welcome, which is basically this presentation, introduce the team, mention our expertise and some of the projects we're involved in, and then give you a summary of what you're going to learn and give you the agenda for today and tomorrow. And lastly, there will be a couple of practical announcements. So the team, and this is mainly the team on the Brunel side, is basically consists of 4 research fellows within my group. So that's Ali Reza Jahani, Imran Mahmoud, Diana Suleimanova, and Amit Arabnejad. 3 of them are here in the call, actually. He's not in the call at the moment. There are also other people who are involved with the development of FabSim3 and the various applications. Those include the co-investigators David Bell, Simon Taylor, as well as Anastasia Anagnostou, Samuel Weeks, and Thomas Hunt. In terms of our background, we have a lot of expertise across different disciplines at the moment, especially about forced population displacement or migration modeling using FLE. We also have some expertise about modeling epidemic events. So for instance, COVID-19 spread, as well as the spread of dengue fever. And historically, I also have expertise in other domains such as blood flow, materials modeling. So think of molecular dynamics and coarse-grained molecular dynamics, astrophysical modeling, and we also have a bit of traffic modeling expertise within the group. The main codes that we currently work with or work on include the FLE agent-based modeling code, the flu coronavirus simulator for COVID-19 modeling on the application end, but on the infrastructure end, we mainly work on the FabSim3 automation toolkit, which automates computational tasks using remote resources. We also co-develop MUSCLE3, and we will also teach the community today about that tool because it's very much a key tool in model coupling. And historically, we have coupled models in a range of domains, including blood flow and migration, for instance, as well as astrophysics. We also, longer ago, we developed a different coupling tool called MB-Wide. That tool is much lower level. It has usually better performance, but it's much more difficult to handle. So our choice today was not to cover that tool, but instead focus on MUSCLE3, which has a formalism around it. It's a bit better structured, better documented, and also is conceptually a bit stronger than MB-Wide. We have a range of active collaborations with UNHCR, the Institute of Migration, and a range of other non-governmental organizations. And at the moment, we're active in 2 projects, Hidalgo, of course, of which this workshop is part, but also VECMA, where we actually do most of the core development on FabSim3 and MUSCLE3. And there are 2 projects that will kick off in September, one on epidemiology called Stamina, and one on migration modeling, which is called IT Flows. And all of these are funded through the Horizon 2020 initiative. So what are we going to learn today? Well, essentially, we want to give you some basic hands-on experience about the FabSim3 automation toolkit and the MUSCLE3 coupling toolkit. And I think the aim more or less is to get everyone who participates to have a working version of FabSim3, be able to run an ensemble calculation and automate a simple workflow, and then with MUSCLE3 to basically get that up and running and run a simple coupled application. So to do that, of course, we need to set up FabSim3 and MUSCLE3, both of them. You may have had some instructions about that already, but if not, do not worry, because there will be more instructions coming soon. It will involve constructing the simulations and executing ensemble simulations, and then also executing coupled models. We have two flavors. So one is with FabSim3, a conflict model using the Flare conflict generator, coupled to a migration model. And the second example is a reaction diffusion equation, where basically you have a reaction and a diffusion model that are coupled together as part of the MUSCLE3 tutorial. The agenda today is as follows. So the introduction is basically what I'm doing at the moment. After that, Hamid will take over and will give a tutorial focused on FabSim3. This will involve the installation of the tool, as well as the installation of the key plugins, especially FabDummy. And then after that, he will present and explain a little bit about advanced configuration. This is important because he will teach you a little bit how to make your own automation scripts, how to curate your configuration so that you can make your runs reproducible, and also how to modify job submission templates for different machines. The last 3/4 of an hour will be about more advanced scenarios and also scenarios using remote machines. And there we will also use the FabFleet plugin. And if you have access to a remote machine, for example, the supercomputer in Stuttgart or in Poznan, then you can also try and use that as part of this, this workshop. At 3:45 British time, so that's 4:45 Central European summertime, we will have a 15-minute coffee break, so you can rest a little bit. And then after that, we have a 1-hour tutorial about MUSCLE3. This will be taught by Ali Reza, with support from all of us in the background. It will consist of a 10-minute introduction on MUSCLE3, followed by a Python tutorial, which basically is intended to just convey some of the core concepts and how to create a very simple simulation. And then we have the last 20 minutes to basically provide support and do a tutorial on distributed execution. And with distributed execution, we don't necessarily mean in different countries, but we mean two separate applications that are coupled using MUSCLE3. Because the workshop is 3 hours and we try to have working examples, all the examples are rather simple. But the tutorial material is online, and there are many more advanced tutorials available in case you want to go more in depth. As part of the email communication earlier on, you should have received our email addresses. So if you want to go more in depth and you have questions further down the line, you can always not only contact us during the workshop, but also afterwards. As for questions during the workshop, I would, actually the number of participants is not very high, so you can choose to actually ask questions by voice if you like. Alternatively, you can put it in the chat. I'll leave that up to you. All right, so, well, I suppose it's time to get started then. So first, we'll give a very brief introduction about FabSim3, and then I will hand over to Hamid for the hands-on tutorial around that. So, what is FabSim3? So the name FabSim is actually, well, Sim is for simulation, and Fab is derived from Fabric, which used to be, and actually still is, a Python toolkit for automating tasks done by systems administrators originally. And the idea of FabSim3 is to have some of these automation functionalities and basically put them in the domain of computational research. And the idea is that just the way Fabric makes tasks easier for systems administrators, FabSim3 should make it easier for people to make modifications to their workflows, make new workflows, couple models together, curate what they're doing. So the idea is to save time and make modifications more easily. The idea is also to store patterns and things that you are using in your computational research, so that there is a copy of it, you can refer to it, you can scrutinize it, and you can modify it and reuse it for a different purpose. The interface consists of one-liner bash commands, which allow for very straightforward access and also relatively easy to memorize. And then there's also curation functionality that allows you to prevent double work, but also to scrutinize and investigate whether the environment was configured correctly, even months after you've run the simulation. The aim for FabSim3 is to make software for the user developer. So it's not end user software. It's not like, for example, the Hidalgo portal or other graphical user-oriented software. It's really meant for developers. And lastly, FabSim3 itself is general purpose, and it has a lot of conventions and best practices, but there are 8 different plugins that have special purpose adaptations. And we have plugins in a diverse set of domains. For instance, we have a plugin, of course, on migration modeling. We have 2 plugins related to COVID-19 modeling. We have a plugin related to climate modeling, and we have a plugin related to earthquake modeling, just to give a couple of examples. Another thing that FabSim3 does is the way the tool's set up. It's basically intended to make using supercomputers roughly as easy as running something on your local host. And I have to be honest there, it does mean that it's slightly more difficult to run something on your local host with FabSim3 than it would be using a local bash script. But it does make using supercomputers a whole lot easier. It also establishes and it can run coupled models using workflow automation functionalities, and it can also run coupled ensembles of models. As mentioned before, it curates input, output, environment information, creates a consistent log, and it also makes it very easy to repeat or reproduce runs because all the run scripts are also stored as part of that. And you can run large ensembles or replicas or combinations of ensembles with replicas using a one-liner command. Now I just have a quick question. Do people know the difference between ensemble runs and replica runs? Oh, it's very quiet. Anyone have any clue?
No, explain it by yourself.
Okay, so basically the two are slightly different. Ensemble runs are basically runs where every individual simulation has a slightly different configuration. So for example, you might, if you have a molecular dynamics run, you might have the molecules at a slightly different angle, or you might run the simulation at a slightly different temperature. But every input for each of these individual simulations is slightly different. If you have a replicated run, then all your inputs are absolutely identical. That doesn't necessarily mean your outputs are identical, because what could happen is that your code is not deterministic, but has a stochastic element, and that would then cause your outputs to be different. FabSim3 supports ensembles, supports replicas, and at least to a certain extent supports the combination of them. Let's see. Okay, lastly, there's a small architecture diagram. I won't go into too much detail on this. But essentially, there are 4 essential parts in FabSim3. There's the backends that allow the tool to connect to your local machine, to remote machines, or even intermediate brokers like QCG broker. And it supports secure shell, but also grid-based approaches such as GSI SSH. There are the plugins that I already mentioned, and there are 3 examples in the bottom right there. And then there are primitives, which are still very much in development. But they're essentially generic patterns that FabSim3 uses to create verification and validation code, uncertainty quantification code, but also these are parts of FabSim3 that can actually be taken out and used in other codes without further modification. Okay. In terms of installation, there are 2 approaches to install the prerequisite packages and software on your system. The first one is that you install all the dependencies in your local machine and then follow all the instructions. And the second option is to download a Docker image with the pre-installed packages. Essentially, what you can see here is the address where you can find the installation tutorial for FabSim3. So please type that in your browser bar, and then you should have step-by-step installation instructions if you haven't installed the toolkit yet. Hamid, are you willing to take it over from this point?
Yes, Derek. Yeah, thank you very much. Thanks for
Okay, you're welcome. I'll stop my screen share. Can you start your screen share then?
Yes, for sure. Let me
Okay.
continue. I think it should be this way. Share it. So, can you see my screen?
Yes,
Yeah.
I can see it. Yeah.
Okay, perfect. Hello, everyone. My name is Hamid, and today I'm going to give the presentation about the FabSim. Basically, my presentation is divided in 3 parts. At the first part, we are going to have some basic installation of the FabSim and test some dummy examples. Then the most interesting part is the writing a plugin for your application. We will write a completely new plugin from the scratch, test it, and then you can realize how you can write your own FabSim plugin for your application. It's not too difficult. It's really easy. You can modify it. And at the last parts, we will look at to the more complicated plugin like the FabFully, and I will explain you how you can add and configure the remote machine for your application in the FabSim. So let's start with FabSim installation. As we prepare the installation, let me just close this part. Okay. As I prepare the installation instruction in this link, I think you all have access to this link. So I assume that you all already installed all the dependency like the MPI and required Python packages. So I am going to take from this point and okay. I think you can see my terminal, yes?
Yes, I'm able to see that, yeah.
Oh, okay, perfect. So I'm going to step by step follow this instruction and then see. So let's go create a specific folder for this tutorial, and then we can clone 2 repository. The first one is a FabSim, and the second one is the file that we will use for the last parts of this presentation. So hopefully, I think the FabSim is almost done. Okay. The first thing that you need to configure your FabSim, it means that the username that you are using and all the addresses in your local machine. We provide automatic configuration. You can use it with typing Python configure FabSim. It will be installed. It will be installed and configure your Python, your YAML machine file. After this, let's do. Sorry, I have an internet connection and it's a little bit low. Today I have a low speed. Okay, I think it's almost done. It should be.
Can we ask how many people managed to install so far? Can you raise your hands in the chat, please?
Okay, Denish is seeing that is okay. Sergey, okay, perfect. So by doing this, you actually okay. By doing this, actually, oh my God, it seems that we have a problem in my system, and I hope it's not the internet connection. Let's hope. Okay. This plugin is configured and set the paths for your based on the installation folder. For instance, in my case, I use these paths, and the result and the config folder will be set. Also, the username for the SSH connection. To install the FabDummy, the only thing that you need, not only install the FabDummy, any plugin. You only need to do the FabSim. Okay, I think as you can see right now, the FabSim is not available. Why? Because after the installation, the path will be added in your bash profile system, but to reload it, we have to reopen the new shell or just source the bash profile to make sure that these new changes are available in the command line. So now the FabSim command is available. We insert in the local host. The command for this installation is install plugin and then FabDummy. So it's clone the FabDummy. The FabDummy is a simple application. Basically, it's just contain FabDummy. I think it's this one. Yep. Okay. I'm still waiting for this. Okay. It's a simple application. Basically, it's just print some text files, nothing else. It just print some text file in your application. Let's look at to the application sides. So basically, the FabDummy is just this parts is just simple text file, and it will be printed on the screen. So if we want to run the FabDummy scripts, we have two options. Simple scripts is here. Is the simple test, which only execute a single job of the FabSim, only execute the simple job of the FabSim and print it in the output, okay? Or write an ensembles. As you can see, there is the execution file of each this local test will be on your FabSim folder and local execution. So if we look at to that part, FabSim and local execution, we can see we have a 3 folder config files, the required file for the application, which is the dummy test here. And the result will be a executable file that you execute on your local system. And as Nick mentioned, okay, we have the FabSim is the automation tools. So basically, you wrap the application with executable scripts. This is a executable scripts. This scripts is generated by the FabSim, and it's only execute your application. So in here, for instance, the application is just showing a simple text file, just that, nothing more. And if you want to run the ensembles, you can run the, instead of the single job, you can run the dummy ensembles and do your tests. Okay, so this is just a simple, and with this test, you can make sure that you already install and configure FabSim in the correct way. So my question to you is that one, have you had any issue with a tutorial that I provided and you installed it before? Did you get any error or everything was fine? Okay, it seems that all people are.
I see that Sergey has his hand raised.
Okay.
I'm not sure if that's from a while ago, but.
Okay, it seems that there is. It seems that all people have a correct configuration of FabSim and they can execute the simple and the dummy test. So,
oh yeah, I just unmuted Sergey, but I think he just muted himself.
The interesting part, yep.
Sorry, go ahead.
Okay. The second part and the most interesting part is that how we can write a plugin for the FabSim. So to do that, I prepared a simple application last night. Is the Canon app is actually simulate the movement of the ball based on some parameter like gravity and velocity and so on. So let's first look at this application. It's a really simple one. So let's do Git. So let's do Canon and just execute a simple one. So when you execute these examples, it's create okay, it's here. It's the Canon app. So it's create the output is the location x and y for when the ball hit the ground, and also create figures and this XY generated in during the calculation of the ball movement. The input files is a really simple one. So basically, we just provide some parameter like gravity, mass, velocity, angle, and height, and other or a resistance, and then based on the simple calculation, we try to see when the ball hit the ground. So this is a really simple one. So let's to write an plugin for this application. Okay. So please let me know if you have any question during this plugin. First of all, we can create a new repository. Let's to call it Fab Sim. Yep, we can call it Fab Sim, I think. Okay, and then public initialize, and we put the Python for this, and okay, Fab Sim, we call it, and create the repository. The first thing that you need to do is, so far we have only the empty FabSim plugin. If you want to add it to the FabSim, you need to add it to the specific file. The file name is inside the FabSim. You need to add it to the deploy, and not application, I think. So far, it's easy. Let's do that. Let's continue the writing the plugin. There is some structure that you need to follow when you want to write a plugin. For example, all the plugins, if you have an application, the applications should be inside of the folder name config files. You can see this config files folder in all FabSim application or plugins. Config files. So now we can just simply copy this Canon application and put it inside of the config file. So let's get rid of this GitHub and README and also these outputs. So now we have this application inside of the config folder. So the next part is to writing the FabSim automation scripts to run your scripts. So to do that, first we need to create a Python file. The name of the Python file should be exactly the name of the plugin. So here we can say Ensemble plugin, and we have a Fab Sim. So we create an exact Python file, sim.py. py. So here is the file that we created. It's the fab canon sim. It should be exactly the same as your plugin name. So when you want to write plugin files, you need also follow the specific, so not specific, some structure. For instance, since that the FabSim should load these plugins and all the files are folded inside of this one, we need to add the scripts and the templates that we are going to use in this plugin to the FabSim folder or FabSim address. To do that, easily you can write or just copy and paste from the prepared plugins, and then add local path and the name of the, okay, I think that should be fine. Okay, these scripts, these parts will be add local scripts and template paths to FabSim. So the next part, the second part, is writing the scripts, writing the task. As Derek mentioned, the FabSim is based on the fabric. So basically here, if we can define the function as a task to be called by the command line. So to do that easily, for each function that we want to add to call it as a task, we just need to add the task and then definition of the function. For instance, I assume that here we want to have a canon sim function or the task to that as an input, it will be, we will pass the application name, the application that we want, and other arguments if is needed. Okay, and then the purpose of this current sim, as I mentioned, is to run the task. We can say, okay, for instance, the FabSim remote machine, that could be, for instance, the local host or the eagle or anything, the task that we needed to be executed, and the application. The application is in the config files. So basically, the application that you copied, this folder is the name of the application. So you need to make sure that you exactly pass this one, because in the application side it will be look for this application. So, and here we can say, okay, is submit a single job of Canon app. Oh, sorry. Let's start writing the other part. The first part that you need is to first update your environment. FabSim, since that is rely on the fabric, there is some predefined environmental variable from the fabric, and also some defined variable in the FabSim. So if we want to do that, we need to also first we need to update this environmental variable. Why? Because sometimes as an argument, maybe you want to, for instance, submit your job with 2 or 8 cores. You can easily modify this type of the variable, environmental variable, by the command line. So to make sure that we, when we want to run the application, we update this environmental variable by the past argues. If we have a past argues, that's fine. Otherwise, nothing will be updated. So the function that used for this part is update. Sorry, not this one. Update environment, and then we pass the args. And so the first part is updating the environment. The second part is to fix some variables or like the address and the other parameter related to the application. So we say with config. So by using this by using the application name, for instance, pass to this application, pass to folder, and our related environment variable will be set. Then, before the execution, because FabSim is just try to prepare your configuration to be executed. First, we need to tell, because we cannot modify and work with the original code. So we transfer it to the temporary folder, and then from that folder, we try to execute and do and make a replica or the samples. So to do that, first we need to say execute put configs and the application. So for this function are provided by the FabSim, you just need to call it, okay? And the last part is executing the task. So as I said, to execute the task, we basically transfer the configuration folder, okay? We transfer this part, okay? But we need to execute the Python code. So to do that, we can easily use the template functionality. Let me to, okay. For each application, each FabSim plugin can have his own templates. What exactly these templates do? If you remember, for instance, in case of the local execution, okay, here, in case of the dummy test, we have this executable file, which called the FabDummy application. So we need the similar for the any application, because we only transfer the source code. So we only transfer this Canon app. We need to prepare the execution mode. To do that, inside of the your plugin, you just need to create a folder name templates, and in that templates you need to create your scripts. For instance, in here we can say Ensemble plugins, let's just say templates, yep, and then say, see, just that, okay. In that template, you need to say, okay, how the application should be executed. The command line is the Python3 canon sim.py. As you remember, is the simple command line that we use it before. I think, no, we don't have it here. Okay, no, that's fine. Yeah, here. So we only need to execute this command. So this is a script that we need to add it. So, but these scripts should be executed inside of the application folder. So we run the application in the we submit and execute the application in the FabSim folder. We need to, but in the FabSim folder we don't have the canon sim py. We need to relocate and transfer to that path. So to do that, we just need to put job results. Just that. This environmental variable is modified and filled by the FabSim. So for each executable application, for each time that you want to execute your application with a FabSim, this job result will be filled, and you will be point to the correct address. Like, for instance, like this one. As you can see, for instance, in here, first it goes to the local execution FabSim result, and this folder, this specific folder for the application, and then run the application. Here we have the same approach. So we say cd to the job result. This job result is an environmental variable. You don't need to care, you don't need to modify it. It will be filled by the FabSim, and then run this command. So where we were, okay, it's here. And so if we want to execute the job, we need to pass the scripts. For instance, we can say script, the script that we use it, and we just created Canon Sim, just that. So we update the environment variable. If we have it, it will be updated. Otherwise, nothing will be changed. With config, we set all the paths to the application. With execute, we transfer the application to the target folder to be executed. And with job, we execute the task. So let's do execute it. For instance, we can say here FabSim localhost. Let's do execute on first.
Make small note in templates. The file that you named, it's has only one N.
Oh, okay. Thanks, Diana. Good catch. Thank you. Okay. Yes. Also, be careful about the name, because you need to make sure that everything is exactly the same name that you use. Yes, you're right. Let me to put it here. Okay. It's better. It makes sense. Make more sense. Okay, and then run it. Okay. Add local path is not. Okay. I think. Okay. Sorry. Add local path. Sorry. Okay. We have an. Okay. I think that this dictionary script Canon Sim, and the job we have a
Script is C.
Oh, yep, yeah. Typo. Okay. And it's executed. So if we go to the local execution folder, which is a local exe, we can see in the result, we have a Canon app. And you see, as you can see, all the files from the application transferred here. This is a script that you write. Okay, this is a script. So if you remember, we use a cd job result. This result, that job results folder filled by the FabSim, and then execute this command. As you can see, we have an output text file, and also the PNG folder, and also the PNG figures for the movement of the bar. Okay, so we can, so far, a single application, a single execution is done, and we can call it with a more input parameters. For instance, let's to look at, for instance, let's to, yeah, I know that is not to use the course. Okay, let's to put course is equal to true. As you can see here, it generated the new folder, localhost 2. Okay, so, and put the application here. Why? Because if you look at to this env.yaml file, And yep, it's here. Can you see, guys, in this line?
Yes, Hamid, yes.
Okay, so the job name template is the template that we used for the job name, folder name, and so on. So when I change the course as the input parameter, the job template name is completely changed. You can easily modify it, this parameter. You can easily modify it for your application and put the whatever you like as a name for the output folders or output executable file. That's completely up to you. If you want to become more familiar with a parameter that we use and we modify inside the FabSim, the only thing that you need, just look at to the env.yaml file in the target folder, and you will see a list of the variable that is filled by the FabSim. So you can easily find, for instance, in here we can see the home path is set to this one. So if I want to execute my application in the another file, the only thing that I need to change is to change this home path address, and so on. So let's go and write. Oh God, why I have it here? Go down. Okay. And so far we have only the single application. And I forgot. Sorry. In addition to the for instance, the inviter parameter, as Derek mentioned, in the FabSim, we also support the replica. The replica is the execution of the same application with the n times. For instance, here we put 3 times. So it will be copied and execute the same application, same input 3 times and store in the output file. As you can see here in the results, these 3 output is belong to the last comment. So we have a replica 1, 2, and 3 for the same application. Okay. Do you have any question? Okay.
Please, if you have questions, just unmute yourselves.
Okay. It seems no one has any questions, so let's move to the...
Sorry, guys. Sorry to interrupt. Yep. I just realized that in the channel, people were not able to unmute themselves, so I just ticked a box that said allow participants to unmute themselves. So I hope that solves this problem and makes it easy for people to unmute themselves and speak up.
Okay, if anyone has a problem, has a question, please let me know. Okay, no question. Let's have and write our ensembles example. So for the ensembles, the first thing that we need is to have because as you know, the ensembles in the executing of the same application with a different configuration. So first thing that we need to do is for the FabSim, we need to create a sweep folder. Okay, and inside of that sweep folder, for each different run, for instance, I can call it run, for instance, run 1. Okay, let's call it run 1. Okay, and based on our application, the input files is here. So just be careful about one part. So let me go to this one and the plugin. Yes, it's here. And the config, okay, and the sweep folder and the run one. So everything that you put in the run folder will be overwrite to your application. What it means, at the first step, all the file and folders without the sweep will be copied. Then for per each folder inside of the sweep, for instance, here we have a run one. For each folder inside the sweep, we copied and overwrite all the files and folders to the target machine. For instance, here we want to rewrite the input files. So we just copy the input files here. And what we can do, for instance, let's to change it to, for example, 5, the velocity to 3, something like that, or 3, just that. Okay, this is a one input file. Also, we can, for instance, copy and paste. Let's call it run 2, and also change this one to, for instance, 9, 10, and put, for instance, 4 with the different values for each run. So now we have a 2 run, 2 assembles, and we need to write the new scripts, new tasks for these assembles. So here we have a Canon sim which submits a single job to the single Java Canon application. Let's to do that, and the second part we can call it samples. Okay, and we say okay, it's submit and app. Okay, Canon app jobs. So let's fix this part. Okay. So for this part, similar to the previous one, we need to do some modification. So first we need to update the environment. Okay. So some parts are not necessary. I will explain why. So for the assembles, we need to pass the application and the sweep directory that we created. You see, we create the sweep directory. We need to pass this sweep directory as an input to for the job execution. So first of all, we need to find the sweep dir pass. So to do that, we can say, for instance, define the sweep dir is equal to find config file pass, I think, yes, and plus the folder name was sweep folder, okay, and also the script. As you can see here, in the previous one, we set the scripts as an input parameter to the job. We also have this option to directly update the environmental variable. For instance, in this case, I'm just scripts equal to, can you see? Instead of passing, I'm just set the value with a hard code, okay? And then we cannot run the job because job function only execute a single job. We need to run another function name ensemble. We pass the application name, sweep dir, and also the arguments if we have it. Okay, and then just that. Let's to check if it works or not. So FabSim localhost Canon ensembles and Canon app. So it seems that it's work, and let's look at the output. The output config folder, Fab Canon, plugins, FabSim, I think it should be here. Okay. FabSim, local execution, FabSim and the results. So the result is, this is a new results. This is a new result. But since that the name of the folder is exactly same the previous one, okay, you see, if you look at to the time changes, data time of modification of each file, you will see these are the completely old, and this one is a new one. We can, for instance, if you want, we can completely clear this folder and then run it again. You will see that you have a runs folder. Inside the run folder, for each assemblers, we have a different output. For instance, this is the output for the first one, and this is the output for the second one, with a completely different value. So it means that the sim settings, you can see 9.10 and 5.3.6. So as you can see here, okay, the inside of the, for each run, we use the original files and also rewrite and or overwrite the files inside of the each sweep folder. For instance, for the run 2, we overwrite this one to these folders. For the run 1 again, we overwrite these input files to the input file, original input files. So basically with this approach, you can easily, without any hard coding and so on, you can easily just have samples of your application and only change what you needed inside of each sweep folders. And also there is other as a previous one, you also can run these samples with Replica. For instance, Replica is 3. So we can see here, each sweep folder will be executed 3 times. So, and this replica, for each replica, for instance, for this run 1, we have a 3 replica of the same input and same execution file. Okay, I think our plugin is almost ready. We can go to the plugin. And just one more thing, I think that maybe that will be better for you. As you can realize, sometimes maybe you see, for instance, you want to run the several examples for your application, and most of times the name is same. The executable file and the executable folder, target folder is named same. Let's look at to see how we can overcome this issue. So as I said, we have this option here to change the job template name. So what we can do for both, for this task or the ensemble task, we can define the, for instance, label. Let's to say empty if we didn't pass anything. And before the updating, we can check if len label is down 0, then env dot. We update this part. We update exactly this part. Env dot updated with a previous format, and also and add the label that you passed at the end. Okay, let's to have the same config here. Okay, and then run again this with a, for instance, label test replica, and run it. And as you can see, this label will be added to your target folder. So you can easily see how you can easily modify the labels and any other environmental variable that you want. The only thing that you need to just look at the ism YAML file and see what's the output, the initial output of your application, your plugin, and then try to modify it by a hard code here. Okay, so any question? Okay, I think the plugin is ready for we can, okay. Oh God, where is this? I cannot see my screen. So, it seems that I have a I don't know why I cannot. Okay, that's not important. Username for this GitHub. Okay, it should be now. It should be available in the repository. Let me just look at it. And yes. So now you have we write a simplest. We write a simple plugins. Use some simple application and the comments. These comments are really common. You can use it. And if you want to have a more complicated plugin, you can look at for instance, the FabFilly plugin or the FabCovid-Sim plugins, where we use the more complicated function into those plugins. Okay. Any other question? Do you have any other question, guys? No question?
It seems everything is clear.
Okay, I think I don't. Okay, so everything is okay. So I'm going to give you 10 minutes. You can just to make sure that you understand everything in these plugins. You can add the plugin to your FabSim plugins YAMLs and install this plugin and then run some samples. If you have any problem, just let me know in this 10 minutes, and then we move and look at to do more complicated plugins. Okay. Is that clear for everyone what you need to do? The only thing that you need to do is just add this. Oh God, this. Go up. Okay, we just need to add this part, these two line in the. Let me find the chat here. Where is the chat? Participants. Okay, I cannot find it. How can I send the message to all?
I think you can just select it in the toolbox, and then at the top you have everyone in meeting. And you can send a message to everyone.
I don't have everyone in the meeting, unfortunately. I don't know why.
Oh, let me see if I can change something for that. Let's see.
Oh, no. I found it. Everyone in the
Okay,
meeting.
very
Yeah,
good.
I found it. Okay. So you just need to add this line to the let me, oh my God, this is to the FabSim deploy plugin YAML. I can write the address here. So you need to add this plugin at the end of this file, and then to install, you can say FabSim, sorry, localhost install plugin and the name of the plugin. And to run the examples, I think you can look at to these files, to this I'm pressing here. To run the single, you can use FabSim localhost Canon app, and for the second one, just Canon Sim ensembles. I think you can easily find it in the Python file.
Incarnation of FabSim was not general purpose. It was for a blood flow code called HemLB, and it was back in 2012. Back then, what they basically did is they used the Python Fabric toolkit to automate the installation of HemLB. So that meant when you were at a remote supercomputer, you would actually download latest version of the code, install and deploy the whole thing live from the internet. All those functionalities are all those base functionalities are still in place. So to, for example, have FabSim synchronize conditionally or unconditionally with a remote data source prior to configuring and setting up and constructing the simulations would be pretty straightforward to implement, actually, because a lot of these remote access mechanisms and remote control mechanisms are already in the toolkit. FabSim does work in the way, however, that you always have to script things yourself. You can take examples and modify them. And for example, I think HemLB still does have a range of FabSim commands that could be ported for this purpose. But yeah, you do have to develop the scripts around it. But I would expect that it takes perhaps a day of development to put something together there.
But do you think that we need to develop, I don't know, a new plugin for the FabSim in order to tackle with new data format or new data source, which is, for example, yeah, this Eurostat for, or maybe we can use exactly existing functionality.
I think the way I would like to do this is if it's a very specific data source, a specific website with a specific format, then we could do that inside the plugin relevant to the application, and we could make a new plugin for that. But the overall mechanism of accessing a remote data source and synchronizing that and providing a local copy, we could actually add that to the base of FabSim3, and then it can be freely reused by any of the plugins. So we could even decide to do that with some very common data sources like Eurostat. I think it would be a very interesting extension, actually, to sort of have a direct integration with external data sources.
Yeah, because Eurostat publishes a hell of data sets, yeah, related to the different aspects, financial aspects, gross product, and many others, yeah. So for example, if you are interested in some specific aspects and you would like to have some reports, yeah, which are updated, yeah, frequently, and whenever you want to have it automated, yeah. So for example, FabSim, yeah, could be a perfect way, yeah, to do this according to the presentation, yeah, given by you, Derek, and Hamid. In order to reduce a human work around it, yeah, so people are not involved in this scenario, in checking if there is a new data set emerging on the portal, for example, but it can be automatically, yeah, organized, curated by the FabSim. So whenever a new data set will emerge, yeah, as some computation is run, and I don't know, some email or something like that, some notification is sent to the author that, okay, you can have a new data set you can analyze, yeah, so in some way.
Yeah, I think it makes a lot of sense, and there are actually multiple possible ways that you could do that. So first of all, for the FabSim plugins, very often configurations are not locally on the machine, but they're actually curated on GitHub. So you could even update the GitHub repository based on updates from the data source, and then you would immediately update it for all users in one go. So that could be very efficient. That could be one approach. The other approach is, for example, the approach we use for uncertainty quantification, and that is just that when you run the command, it dynamically generates all the simulation inputs. In the case of uncertainty quantification, we use EasyViewQ to generate all the specific input files for all the different runs. But we could, of course, have a similar approach, but then integrating an external data source to insert.
Okay. Yeah, this is just a general idea, yeah, I have in mind. So because I faced this problem some time ago, and basically it was very tough, yeah, to check it manually, yeah, with some frequency. But if it could be automated in this way, and yeah, it would be a perfect solution.
Yeah, and also specifically for FabFleet, we actually do have some integrations with remote data sources. For example, the Armed Conflict Location Events database, and we are already pretty far in sort of developing and testing commands to automatically download that type of data. So we've actually already done it with a few data sources.
Also in Hidalgo, yeah, we can use it. So whenever new data come from, I don't know, from ECMWF or from sensors and from any city, we can yeah, run this simulation automatically, yeah, because FabSim, I suppose, can check that something changed from with some frequency, I don't know, every minute or so, and whenever changed, yeah, we can run the simulation.
Yeah, I mean, I guess the nice thing is that it would all be part of the command to start simulation. So you only need to check it when you want to start a simulation. Unless the data is enormous in size, then you could go for a different approach. But I guess that's very situation specific. But yeah, I do hope that all this clarifies a little bit about sort of the possibilities and constraints around integrating external data sources. But for sure, there are quite a few options there that we can pursue there for Hidalgo.
But the thing that we can cover something more than only the fetching data and running the simulation, I don't know, maybe we can also include, yeah, in this scenario, I don't know, something like the data analytics as well, yeah.
The data analytics is definitely part of FabSim. We don't always emphasize it as much because very often the data analytics is done locally, but in a lot of the different examples that we also present today, but that you also find in different plugins, there is a lot of data analytics going on. Data reduction, collation, conversion from simulation specific outputs to generic variables inside FabSim, or post-processing scripts. So there are a lot of those kind of functionalities that we actually have available within FabSim for specific purposes.
Yeah, but I thought that FabSim could be only like a manager, yeah, which would be responsible for organizing this path, the stream of the data from the simulation to simulation. Yeah, okay, please go on.
The base tool does exactly that, and it's usually in the plugins where people start integrating specific processing scripts and making workflows with the conversions and all those kind of features. Of course, yeah, the base layer of FabSim doesn't contain specific data for converting, I don't know, conflict event data to FLE input data, but the FabFLE plugin would contain such information. So very often these data processing aspects you find with the specific plugins, but then they rely on generic FabSim functionalities to make various parts of it easier.
Yeah, okay. Thank you.
Any other question? So let's go to the third part of the this tutorial. To do that, first I would like to talk about how we can configure I think it's more useful for our people, how we can configure the remote machine and submit our job into the remote machine. Basically, let me to open the deploy and the mesh is that. Yeah, okay. Basically, all the configuration of the remote machine are in these two files, machine yams and the machine user yams. Machine user yams will be override the specific environmental variable for your application or for your account and so on.
Hamid, sorry.
This month, yeah.
I think your screen is frozen. Are you showing anything at the moment?
Yes, I'm showing.
We still have okay, now it's
Can you have it? Okay, sorry. Okay, these two files, the important one is a machines.yam file. It contains all the environmental variable for each remote machine. You can define your own environmental variable or use the predefined environmental variable. For instance, like if you want to submit a job with a virtual environment in the remote machine or not, for instance, you have an application and you cannot install all the Python library in the remote machine, so you can use the virtual environment to submit your job. Or the number of cores that you want. As you can see, the default is 16. That's why when we submit a job, we thought changing the cores, at the end, we always have the 16 at the number of the cores. And also home pass template, which define the pass of your account in the remote machine. Yes, I know maybe this is not, maybe these are not same for our remote machine. That's why we can redefine and change this environmental variable. For instance, let's to look at to this for one example. Let's to look at as you can see, we have several machines, and for instance, we have a Supermode, we have a Archer machine for the configuration with Archer machine, and so on. You can easily read these examples and configure your application, your remote machine without any problems. Let's look at to the yep, this here, Eagle Hidalgo. This is Eagle Hidalgo is the entry that I created for the remote machine that we use within the Hidalgo. Okay, so basically what we need, for instance, the remote address that we connected and submitted jobs, we need to use the specific address. We change it here. The home template pass, for instance, within the Hidalgo, the home template pass is the home users and your username. Okay, but for instance, well, on the same machines, I have another account with the Wekma. It's another project. In that machine, I have a different home pass template, so you can easily change this to without any problems. Okay. Also, the bash header is the header that you will submit and attach your application to to the remote machine. As you remember, when we submit jobs in the local machine, we only submit it with a bash. So we only attach the simple bash scripts to our application. However, for the remote machine, we need more instruction. For example, let me to look at deploy template and Slurm. Let's look at the Slurm again. For instance, for the Slurm machines, we should, when we submit a job, we should set some parameters. For instance, in here, we need to define the number of nodes that we want to reserve. We need to define the task per nodes. Here is equal to the cores. So if you submit jobs with a specific cores number, this cores number will be replaced by your value. We need to set the time job, wall time for each job, and so on. So basically, these templates provide simple JavaScripts that will be attached to your application and then submitted to the remote machine. For example, let's do submit a single and simple job like we already have it here. Is not okay. Go up. For instance, go down. FabSim, we can use the, for instance, submit a job in the Hidalgo account, and then say the job name. I'm just going to copy and paste to make sure everything is exactly the same, and submit a job. Okay, let's see that it shouldn't ask for this one. That's really interesting because I removed the password from my account, and it should be okay. Oh, sorry. I know that's the problem. So before we submitting, we need to also specify the variable, some variables in the machine logs. For example, here we need to specify my account name. Let's to put it, my account name on the Hidalgo is Hamid, and this one is not necessary because we are not going to use that part. And then submit it. Cannot low level. Okay. Let's see. It seems that my connection has a problem with the port 22. That's really interesting. No, I cannot connect it to this remote machine for some reason, which I don't know. Config. Okay, see that I have a problem with let me see if I can connect it. No. I cannot even log in. Maybe it seems that there is a problem with the Eagle machine because I cannot connect it to this machine. That's really interesting. Let me check the another account. No, none of these accounts is working, and I cannot connect to the.
Martin, do you perhaps know if there's anything specific with Eagle at the moment?
I just checked it right now, and I can connect it, yeah, through the SSH. Yeah, very.
That's really
easily.
Interesting because I cannot connect it. Let me to. That's really interesting. SSH.
Basically, I'm connected. I'm on the Eagle now. Connection refused. Yeah, there is something with I suppose with the firewall, but definitely not on our side, I believe.
Okay.
I'm also connecting from home, so I'm not in the internal network.
Okay, that's it. Because I'm connecting within the home, and I think that should be work. I'm not sure if Derek, can you just connect it from your?
I'll give it a quick try. Just give me a second.
That's interesting.
For my Brunel desktop, I'm able to connect to Eagle.
Okay. That's
I
really,
can
I
connect
don't know
to-
why. Okay, why my account is blocked?
Can you ping the eagle.man postman.piro?
Let's do SSH with V and we see the verbose.
Yeah.
No connecting address, connection refused. I think for some reason maybe I'm blocked, which I don't know why.
Are you trying to connect directly from your MacBook right now, right? Correct?
Yes. I'm just check it with my Ubuntu, and in the Ubuntu it works. That's really interesting.
Ah,
That's
okay.
really interesting. It seems that for some reason this port, my address is blocked. I don't know why. Maybe because I'm using the mobile data. I don't know.
Oh, that is possible. Yes, if you use mobile data, that can be the case. Yeah.
I'm using the mobile data. Okay, maybe we cannot have these examples right now here, but let me just continue the explanation. Okay, so here you can define the remote machine that you want. For instance, if you have the Slurm machine, you can, for instance, create the new machine here and call it, for instance, Eagle test. And we already provide some basic functionality from is here. It should be here in the parent entry. Okay, so for instance, how we can have the get a report, how we submit the jobs, and so on, how we cancel the jobs, how we see the list of the jobs in your queue, and so on. Okay, so you can use that part. And if, for instance, in your case, if you have, for sure, you need to update this remote address, maybe you need to update this home template path and other part, or the budget that you have it in your remote machine, you can set it. Also, you can set the partition name that you want. There is a lot of possibility. There is a lot of flexibility here. You can test it. And the other part is this part. It's FabSim let allow you to load and unload the module that you want when you submit a job to the remote machine. So, for instance, in this case, I specifically wants to load the Python 3.7.3 and Open API and unload the previous one, Python, which is, I think, is a 3.5. So you can modify it and have a lots of the flexibility when you want to configure your remote machine.
Amit, what exactly is this budget is? Can you elaborate a little bit more?
This budget is the I think the account backend account budget that we have it from the Vecma account. Sorry, from the Hidalgo account. It's a 394.
Okay.
Yes. For instance, for within the Vecma or budget account is the Vecma to 219. I think it should be 220. Yes.
Yeah, so that's the core hour allocation basically, and every supercomputer has a different system for that. So sometimes it's per user, and sometimes it's a project, and it's a pooled account.
I'm sure, Martin, you send this budget accounts number to all of us.
Yeah. It looks like a grant number. Yeah.
Yes, it's a grant. Yes, you can say. Because you see,
Yeah, exactly. Yeah, but I found it is yeah, related to the accounting and maybe with some money. Yeah, your account. I don't know. CPU hours or something like that. Yeah, this budget term a little mislead me, but okay.
Well, yeah, CPU hours is money, right?
Yeah, of course, everything is money. Yeah.
I mean, I just small anecdote, but I remember back in 2008 we were using a Dutch supercomputer, and then we accidentally got billed for the hours that we were using, and my supervisor at the time was quite surprised to get a bill for 28,000 euros.
Yeah. Everything is money. Only love is pure. Yeah.
That's right. Okay, that's fine. And also you can you can also define the new environmental variable. For instance, in here we define the run command equal to MPI run. Okay. For instance, in your case, maybe you have a Java command, you have a Java application. You can define the environmental variable here, okay, in the YAML file, or you can define the environmental variable inside of your plugin code, and then use it in the template files. For example, let me to move and look at to the second template is the Fab dummy. Fab Philly. For instance, this is a more complicated template. For instance, in here, in the P-Philly, in the for the parallelization of the Philly, we can, in addition to calling the Python tree, we also need to run and execute the MPI run. Okay, so basically here we create the environmental variable named run command, and we call MPI run application with n as a number of the cores, and these cores will be attached to this script. So when you submit a job with, for instance, 20 cores, 4 cores, or 8 cores, this script, this variable will be replaced by this. So as you can see, you have a lot of the flexibility that you can modify and decorate your application to be executed in the local machine or in the remote machine. So let's to move and take, okay, I think we already write the plugins, we all tested. The second one, the last part is the FabPhilly plugin, and the local execution is exactly similar to the plugin that we just wrote. You can use the FabSim. For sure, for the installation, you need to use the local host. Install plugin is the name of the function, and the FabPhilly is the name of the plugin that you need. As you can see, as you saw it, these plugins, all plugins that will be installed and downloaded in the plugin folders. And then to execute it, for instance, you can say, okay, Philly configuration and simulation period. Why we have this approach? Because if you look, because in the FabPhilly PY, which is a really complicated and more advanced plugins, as you can see, we still have import some functionality from the FabSim. We add the local pass function here to be which added the local scripts and the template to the FabSim. And let's to look at to this Philly. So for the Philly, here we have a more complicated and advanced function. In this function, we have a config. Is the name of the folder that we have in the config folder, and the simulation period, which is the mandatory, is that optional. So you have to pass it, and then with these parts, this application will be executed. The interesting part is here, the simulation period. As I said, you can set the environmental variable in the machine YAMLs, which is completely fine, or set it inside of this, inside of the with a hard coding. For the hard coding, you have two options. The first option is, for instance, you can write n dot simulation period equal to simulation period. This is the first option. Or use the update environment functionality and pass the environmental variable as a dictionary. The name and the key value and the value, just that. And let me to look at this one. And you see, you also have you can change the some script, some environmental variable here. Again, we pass it as an input to the job. For instance, a script changed is a Philly, and for instance, for the P Philly, we have a different scripts. I think, let me to find the P Philly. Yes, for the P Philly, we have a different scripts and so on. So everything is completely customizable here. You can do, you can have a different template for the different situation, and then call it and run and execute your application. So for instance, for the to execute the application, you can run on the local host for sure. You can run the Philly, is the name of the task. Again, all these function, if you want to use this function as a command line, as a task, you need to make sure that you mark that function as a task. This is required by the fabric. And then we pass the config folder and the simulation period. After the result, maybe we can run it, just run a simple one, local host, Philly, Mali. Equal to 10, I think. I put a 10 to make sure. Okay, it seems that, oh, I have a misstep here. I have a simulation. I think I missed this part. Oops. There is an error here that says that export Python field. Okay. The problem you can see, as you can see here, FabSim gives you some report on the output. The problem here is that we didn't define the field location. Okay, because in our template we have a field location and we didn't define it. To define that field location, we can go to this machine user on the local host and says, okay, field location, and we need to make sure that our field location is correct. As far as I remember, the field location was in the Hidalgo tutorial folder and the field. I think, no, that should be, why I don't have it. Local host, field, Mali. So it was too fast, 50 to be executed. So the output will be here. As you can see, it's generating the output format, output folders. And I think for the FET application, the output will be written in the output CSV file. Yep. And for all 15 days, we have the data with the simulation and the original data, and also the error bars. So this is a execution, is like the remote machine. You just, instead of the passing the data to the remote machine, you execute it on your local host. Then you can use the FabSim localhost fetch result, and with this one, FabSim localhost fetch results. So it will be this command will download it. We say download it here because sometimes we may want to connect to the remote machine and sync and download all the results from the remote machine. This command will be download all the results, all the executed results in the FabSim folder. Go back and results. As we can see here, the result is here, and then we can do the post-processing part. So if you submit a job in the remote machine, if you want to have a post-processing or download the jobs, first you need to fetch the result, and then the result will be added in this into the FabSim3 result folder, and then you can see what's the output and working on the results. Okay, for instance, in here we have a post-processing part. We call it let's see, sorry, why I cannot move it. Okay, we call it localhost pellet output. This one will be create a pellet for each application, for each for each conflict location, and inside of the output it generates several output folders, several figures that you can see the error that you achieved with obtained with our simulator and the original UNHCR data. Okay, I think that's it. Okay, I think in this tutorial, you should be able to write a simple plugins for your application and run and submit some simple job and assemble jobs. I'm suggesting if you want to use to look at the more advanced techniques, I'm strongly suggest look at the fabfili.py file and the template folder that we created for this fabfili, because in the template folder we have a lot of the complicated scripts. You can look at those scripts and easily understand how it's work, and maybe you can use it in your application for your plugin. Okay. Any other question?
Maybe not a question, but
Yep.
some idea. Yeah, I get
Yes.
in the meanwhile. Do you think it is reasonable to use this FabSim for facilitating this data analytics benchmarking we are going to make for this two methods, HPDA methods developed recently? The one of them is of course this local extraction graph. The second one is SVD method, but we at the moment, as I reported during the WP3, we are preparing the environment for both, and basically we need a tool which could facilitate this process by generating a different data sets and different set of parameters, and basically run this methods in the PyTorch. Do you think that we can manage it using the FabSim?
Amit,
yeah, please,
Martin, sorry, just to interject very briefly. We are overrunning with this session by about 12 minutes at the moment. Would it make sense that we have a break right now and then we pick it up in 15 minutes, but then Amit, you could discuss this with Martin right now still?
Yeah, it's completely fine with me, yeah.
Amit, is that okay with you as well?
Yes, for sure.
Okay, so in that case, we'll have a break until I suggest 4:10 or 5:10 Central European Summer Time, so about 12 minutes. And Amita, Martin, of course, feel free to continue the discussion, right? But then other people can take a short break if they like to.
Yeah, perfect.
Yeah, thank you. Okay, Martin, about that part, I'm just wondering what's the exact workflow that you want to execute it. I assume that you just need to, I assume maybe you just need to have a simple script to download it, do some post-processing, and then upload it somewhere, yes?
Yeah, something like that, yeah, but...
and you are going to do this frequently, or it should be executed as a background job in the remote machine?
Maybe not frequently, but for the very vast set of parameters, I suppose, yeah?
I think it can be easily supported by the FabSim if it's not going to, for instance, run it in the background. What I mean is that you have a background, the process always, and every time that you feed a new data, it automatically detected and then apply our analysis. I think if you just if the process, if this workflow should be submitted or should be applied by the person or by the user, you can easily use a FabSim for that part. Okay, it's really easy. It should be really easy.
Yeah, but so I suppose the FabSim is able to run any application, yeah, which is
yes, it's able to. Martin, maybe there is a misunderstanding here. It's not running the application. It's decorating the application, preparing for the execution.
Yeah, exactly. But it prepares the data, input data, and maybe set of parameters as well. But we can, I suppose that. We can also run this application, or this is something which is beyond the scope.
Yeah, we can submit it for the execution. Okay, for instance, in the machine or in the target machine or in the local host. Okay, but FabSim generally by itself it doesn't execute anything. It just prepare it, decorate the application, and transfer it and submit the jobs. That submission, maybe if it's in your local machine, it will be executed by the bash. If it's a remote machine, it will be submitted as a single job.
So okay, so as an output of the FabSim, we may receive a set of let's say folders where all this input data along with the parameters are stored, and based on that we can run our simulations, yeah.
Or you can run the simulation within the FabSim, because after the preparation you can define in the script, in the template, that for instance do this job, for instance fetch this result, do this post processing, okay, and then execute these commands.
Exactly, this is what I expected. Yeah, thank you. But to be honest, there is, the configuration is not that very easy, as Derek said on the beginning. It is for the developers, but I expect could overwhelm me. Yeah, so I would appreciate if you could help us. Yeah, with this
for sure.
With this preparation. Yeah, of this testing
if
environment.
We know, if we know the workflow, how you can, for instance, for the single job, what's the workflow, what's exactly you're doing, we can easily convert to the plugins and you can use it.
Yeah, so once it will be established, we contact you. Yeah. Okay.
Yeah, Martin. Usually our approach is, so historically we would organize a little hackathon to get people started with making a plugin. What we find is once people have established a plugin, they find it very easy to extend it and work with it and enhance it independently. But to get people started, historically, we would organize a one-to-one meeting or a hackathon. Of course, because of the pandemic, that's a little bit more difficult. But I think we could still have, say, an online work meeting, and for sure one or two of us can provide direct support for the application. That's no problem at all. That's actually what we're used to doing. We know that the initial barrier is a little bit higher than the learning curve after that initial start. So we're always very keen to give direct support at initial bump, and then usually after one day or so, then yeah, things are pretty good.
Yeah, happy to hear it. Yeah, thank you.
Yes, because I think based on my experience and the writing the plugins, basically the first draft of the plugin maybe takes time, but after that you can easily, because you only work you only modify the templates or modify the input files and so on. So
yeah,
everything should be easy for you.
Yeah, once it is ready, yeah, or I mean prepared by you, for example, Happy. I suppose we can modify it very easily. But to be honest,
for
preparation from the scratch,
I would be happy.
Yeah, thank you. Yeah. Okay, let's make this a few minutes break, and I'll be back soon. Yeah, thank you.
Yeah.
Let me share my screen. Okay, can you share my screen now?
We can see your screen.
Okay. Shall I just start, or waiting for others to join again?
I would recommend to start. I think that it's 10 past, so yeah.
Sure. So hello everyone, my name is Ayerza, and this is the second part of this workshop. In this part, I'm going to present something about a MUSCLE3 introduction, and how to install it and how to create your files, and then we will discuss a little bit about distributed execution. MUSCLE3 is the third incarnation of the multiscale coupling library environments, and it's the successor to MUSCLE2. Its purposes are to make creating coupled multiscale simulations easy, and to enable efficient uncertainty quantifications of such models by using an advanced semi-intrusive algorithms. And it can be used from a non-distributed but parallel mode in a single short Python file to the distributed mode, where the manager and computer elements instances are started on multiple nodes in a cluster. And also I have to add that MUSCLE3 uses the multiscale modeling and simulation language, which is MMSL, to describe the structure of a multiscale model. And it can be expressed in the form of a diagram, but it's not yet implemented, or as a YAML file, which they name it yMMSL. And it is both a convenience for people and also software. And MUSCLE3 actually consists of three components: libmuscle, yMMSL Python, and muscle manager. libmuscle is a library that is used to connect compute elements implementations, for instance, for new or existing models, to a coupled simulation. It offers functions for sending and receiving messages to and from the outside world. And the other component is yMMSL Python, which is a Python library that contains all class definitions to represent MMSL model description, and it supports loading a yMMSL file and converting it to the objects, and also saving objects to a yMMSL file. And the third one, which is very important, is the muscle manager. It's a central runtime component of MUSCLE3. It is started together with compute element instances, and it also provides a central coordination point that the instances use to find each other. In the current status of MUSCLE3, it is currently supports Python 3, C++, and Fortran. And it currently provides the following features, which are coupling different submodels instances based on an MMSL description, spatial and temporal scale separation and overlap, especially for a macro and micro coupled model with time scale separation. And in that case, usually the micro model needs to be run once for each time step of the macro model. The third one is settings management. And most models have some or many model parameters and other settings that determine how to how the simulation can proceed. And usually in a large coupled simulation, it may be so tedious. So this feature can help us to couple with that. And the fourth one is the most powerful feature of the MMSL, is the combining feature. And MUSCLE3 has the ability to arbitrarily combine all the above features in a single model. Okay, for the first hands-on, I'm going to install MUSCLE3, and it will install all Python-based components of the systems. For instance, a Python version of libmuscle, yMMSL Python library, and the muscle manager. But bear in mind that it requires at least Python 3.5. And since MUSCLE3 is on PyPI as an ordinary Python package, it can be installed via pip in the usual way. So I can show it to you now. Okay, just I suggest that you make a virtual environment by Python MUSCLE3 underscore virtual environment. And then you need to activate it. Okay, now you're in virtual environment. And then you need to install and upgrade pip, setup tools, and wheel. Okay, because I have already did that before. So now you just only need to install MUSCLE3. That's it. And you can easily install MUSCLE3 by entering these 4 commands. So I suggest you do it right now with your terminal, and it's very easy to follow. Okay, if you don't have any question, I will go for the next part. Okay, in this section, we'll look at an example of how to use MUSCLE3 to create a multiscale simulation in Python. And please use the below link to access the source code of the given example. And if you want to, you can do it now, because afterwards we will use this repository and follow the other commands based on that. Let me just share you the, sorry, link. Okay. Where is the part with sending?
Put your mouse a bit up.
Oh, chat, yes.
Up here.
To everyone. Yes. Okay. To do that, I already have it here. Just run make. So After that, so let me close this here. Just build and activate your virtual environment. So it is activated now. And the last part is just running the reaction diffusion.py. Okay, as you see, this is the results of reaction diffusion.py, which are first dimensional grid. Okay. Do anyone has questions regarding running this file? No, I guess not. Okay, let's move on to the rest of the file. Okay, as you saw, this example is a reaction diffusion model on a first dimension degree. It consists of a reaction model coupled to a diffusion model in a micro fashion. Diffusion model here is the macro model, and reaction model is the micro model. In a macro model, micro model with a time scale separation, the micro model does a full run on many time steps for every or each time step of the macro model. So in this case, maybe a macro model would wait for the micro model to send some messages to it. Therefore, the macro model effectively calls the micro model before each state update and sending the current state and using its output as an input for the state update operation. Okay, and the next part, which is very important and it's very usual, it's importing headers. As you see here, we are beginning our script by importing some required libraries, which are orderdict, logging, and OS from the Python standard library, and also NumPy, which provides a matrix math functionality. The reason why we imported orderdict is that usually dict module is not ordered for the old versions of Python, and so to have been adopted with the older version of Python, it is suggested to use orderdict and import it. And the next is you need to import a grid instance and message from LoadLeveller. Instance will represent a model instance in the larger simulation, and a message which represents a muscle message as passed between these instances. And the next part is LibMuscle .run _ simulation function, which allows us to run a complete simulation from a single Python file, as opposed to having to start different instances and the manager separately. Okay. As a simple submodel, let's look at the reaction model. It is defined as a single Python function that makes that takes no arguments and returns nothing. And for do that, the first step in a muscle model is to create a live muscle instance object. As you see here in the reaction, the constructor takes a single argument, which is a dictionary that maps operators to lists of ports. And these ports are very important because they are used by submodels to exchange messages with the outside world. And they can be input ports or even output ports because they are exchanging together, but they cannot be at the same time input and output. So in this model, we have a single input port named initial state, as you see here. And it will receive an initial state at the beginning of the model run. And we also have a single output port named final state that sends the final state of the reaction simulation to the rest of the simulation. Sorry, I forgot to mention that it is very advisable to mention the data types you're going to use in your arrays. And in here, we have a list of floats. Okay, the next part is reuse loop. Now that we have an libmuscle instance object, we can start the reuse loop. In multiscale simulations, submodels often have to run multiple times. For instance, because they are used as a micromodel or because they are a part of an ensemble that cannot be completely parallelized. So in order to accomplish this, the entire model is wrapped into a loop. And when this loop ends depends on the behavior of the whole model. And it's not easy to determine, but fortunately, Muscle will do that for us, and it will call the libmuscle instance reuse underscore instance method to do that for us. Okay, so the next part is initialization, and we are going to see how we can specify the settings and receiving the messages. In the first part of the model in which the state is initialized, pretty much every model has such an initialization phase at the beginning. So in Muscle's abstract idea of what a submodel does is the submodel execution loop, and this part of the code is referred to as the finit operator, as you see here below instance.reuse underscore instance with italic and commented blue fonts. And the other are the total time to simulate, the time step to use, and the model parameter of K. And they can be generic, but it is also advisable to have separate for macro and micro separately, and I will explain it later. So the message data attribute also holds an object of libmuscle grid, which holds a read-only numpy array and optionally a list of index names. In the reaction diffusion model, we don't have a long list of index names. We only have one index name, which is X, that you can see it later, but we can take the array and then we need to make a copy of it for U. Because in that case, without calling a copy, you would end up pointing to the same read-only array, and we would got error message. And finally, we will initialize our simulation time to the time at which that state is valid, which is contained in the timestamp attributes, as you see here is a t underscore max. Okay. The next part is the state update loop. Having initialized the model, it is now time for the state update loop until reaching the maximum time. And if you see at this code, it's very familiar. And on each iteration, update the state according to the model equation. And this update is called operator S in the submodel execution loop. And in this model, it is determined entirely by the current state. So operator OI, which comes before S, provides for observations of intermediate states. In other words, here is where you can send a message to the outside world with the current state. And in this case, the OI operator is empty, and we are not sending anything. Okay, now it's time to sending the final results. After the update loop and at the final state, it is time to share it with the outside world by sending it on the final state port. This part of the code after the state update loop is known as OF operator in the submodel execution loop. And it specifies the port on which to send and the message object containing the current simulation time, the current state, they all converted to a plain Python list. And the optional second pointer is a second timestamp, which is set to none here, but you can have it in times that the timestamp between the macro and micro are not same. Okay. The next point is a MUSCLE3 uses message pack to encode messages between models. And message pack, as you know, is a binary encoding format which can be thought as a binary version of JSON. And that means that the message can be integer, float, Boolean, string, or the other one like dictionaries. And like with JSON, these can be nested, so you can send a dictionary containing lists of floats, for example, to the other instances. And since sending grids is very common in these kind of models, MUSCLE3 supports sending NumPy arrays directly, but as you saw in previous slides, we wrap our array U in a livemuscle.grid object. And finally, to use your own encoding, you can just send the bytes object, which will be transmitted as is with minimal overload. So this concludes our reaction model. As you saw, submodels that are used with MUSCLE3 are very much look like they would without it. And with one additional variable, one extra loop, and a few send and receive statements, you are ready to connect your model into a larger simulation by using MUSCLE. So it's very easy to use. Okay, the second model is diffusion model. Its overall structure is same as the reaction model, but it has a few additional features. And the first of these are OI operator. It sends macro submodels state to the outside world on every time step. And the message simply contains the state, which is converted to a libmuscle grid. It is sent on the state out port. And the second timestamp gives a simulation time for the next message that will be sent on this port. Since our time steps are fixed, this is easy to calculate, and we do need just only to take care to send none if this is the final state. But if the time scales do not match exactly, then the number of messages sent by one submodel may not match exactly to the number of messages that the other submodel is waiting to receive. So to avoid that, we can have the second timestamp and avoid this problem. Okay. It's time to receiving messages with default. As you see here, the diffusion model, which is a macro model here, will need to receive inputs for its state, and it will receive it from the macro model. And that would happen by calling libmuscle.instance receive function. You can see here we have a default message which is returned if the port is not connected. So in this case, MUSCLE can go on without receiving anything from the macro model. The next is we will check that we didn't receive message from the future. The point is this might happen if the macro model runs for longer than our macro model timestamp. So in this case, the number of steps are fixed so that this warning will never be emitted. So, however, if the macro model runs until it detects convergence, then it can happen that it runs for longer than the time step of the macro model. and that would indicate that there is no time scale separation anymore. In that case, the results could be wrong and a warning is appropriate here. And as you see, we have a warning which mentioned receive a message from the future. And then we are going to copy the received data. LibMuscle objects contains a read-only array, and we copy it in the U just like we did before. And bear in mind that you can use global variables to communicate between models, because if you do that, so you can't run on separate programs on different computers. We have another operator here, which is S, and it calls the Laplacian function, which is not shown in this presentation. And if you see at the script, you can see the Laplacian function. There is no requirement for a submodel to be a single function, but you can split it up and call library functions and so on. So there has to be a top-level function. However, if you want to run more than one submodel in a single Python program. Also, you cannot share any data with other components other than by sending and receiving messages. And okay, we have reached to the almost final state. Here we have the diagram, which is a gMMSL diagram of the reaction diffusion model. With both models defined, we can instruct MUSCLE3 on how to connect them together, and we do this by creating an object of type yMMSL function in configuration, and which contains all the information needed to run the simulation. It often helps to draw diagram first, but the problem is, as I mentioned, it's not implemented yet, and it is advisable to use yMMSL. It shows that there are two compute elements named macro and micro, and you can see the input and output ports here and how they can send and receive messages together. And as I told us, since these diagrams are in Python, to describe the model in the code, the yMMSL library is used to create a set of objects from a description. So to do that, the name of a couple elements is used by Muscle as an address for communication between the models. As you see here, we have a diffusion model as a macro and reaction as a micro. And next, we need to connect the compute elements together. And this is done by conduits, which have a sender and receiver. And here we connect a sending port, which are state out on compute element macro to receiving port initial state on compute element micro. And the compute elements and the conduits together form a model, which has a name and two sets of components. Okay, the other section is connecting the submodels together is defining the settings. So to define the settings for simulation, we can use orderdig to make it useful for editing and quickly finding things. As I told you in start, even in all the Python versions. And note that there are two duplicate names between the two models, which are Tmax and dt, but with MUSCLE3, you can create a global setting. But here, we have a specific setting that defined different names for our models, which are micro Tmax and Tmax for micro, and also Tmax for the macro. And the model and settings are combined into configuration, which contains everything needed to run the simulation. And the configuration object is also the Python side equivalent to yMMSL YAML file. Okay, to launch the simulation, MUSCLE3 has a small facility for running the whole simulation from a single Python file in the form of the libmuscle.run_simulation function. And here we make a dictionary that maps implementation names to the corresponding Python functions. And we then pass the configuration and implementation to libmuscle.run_simulation function. And it will start the muscle manager and the implementations, and then wait for the simulation to finish. And just note that this will actually fork of a separate process for the manager and for each implementation, so that this is a real distributed simulation, albeit on a single machine. And that makes this mode of operation a more realistic test case for a real distributed run on a HPC machine. And for log outputs, you can just easily write a Python 3 reaction_diffusion.py to run this script. It will pop up a plot, as you saw, and showing the state of the simulated system over time. And if the point is, if you are on a machine that you don't have any graphics support, you can use this command and you can disable a graphical output. Okay, so the next thing is there are 3 log files in your directory, which are muscle3 manager.log, muscle3 macro.log, and muscle3 micro.log. And these contain all log outputs for the manager and the submodel instances in your directory. Okay, this part is finished. Do you have any questions? Hello guys, can you hear me?
Okay. Yeah, we can hear you.
The last part is distributed execution, and in this section we will briefly explain how to go from a simple macro multiscale model with muscle3 and running it as a single Python script with distributed simulation. It's very easy. Everything is done. You just need to go to the examples directory and make Python. So I'm going here, just write make Python. The only thing is you need to define the muscle3 home, and I do it here and write Python. Okay, and you only need to write this, run this bash files. It was supposed to run right now. Oh, maybe. Let me run it one more time. Okay. Not sure what is happening right now, but that is the results of the running this one. Sorry. And or even you can start the manager and run a muscle manager reaction diffusion yMMSL, and then starting your instances separately, and the simulation will start to run. And once it's done, the instances disconnect and the manager shuts itself down automatically.
Ali, sorry to interrupt, but if you like, I can explain the figure you showed a second ago, this one.
This one?
Yeah, exactly. So this is basically diffusion over time. So if you look at the y-axis, you see the time of the simulation. It starts with 0 at the top, and then it goes to 0.12 at the bottom. And then on the x-axis, you basically see a spatial axis. So it's a one-dimensional axis. And then what you can see is basically the change in concentration, which is in minus. So basically the yellow part is the most dense section. And what you can see here basically at the top is that you have very concentrated pieces of a certain liquid. And then over time you see it spread out. So you see the cones widening as you go down the plot. So that's just to explain to everyone what this result actually means.
No, thank you, Derek.
Okay.
So just a little bit explanation about using this script. Let me show you here. This is the reaction diffusion script, diffusion underscore diffusion. And then this is the bash file. You see here on the distributed manner, we run separately these files, reaction and diffusion. So in other words, we run a macro and macro with the same script here. And in our case, we use it to couple the macro model and macro in South Sudan simulations, and we use this guideline as the benchmark how to use muscle tree coupling into FLE simulations. But if you want more information about muscle tree, there are a lot of references. First one is the reader docs, which I use it for preparing this slide, and it explains more about how to implement muscle tree in Python and also in C++. And also Lawrence and Alphonse published a paper, and you can access to that paper by clicking on this link. And there's a GitHub repository for muscle tree where you can find all the relevant files and scripts in there. Thank you so much. I'm waiting to answer any question you might have.
Okay, we one question, yeah. We seen that muscle3 is it seems to be very useful, yeah, for this micro and micro model, yeah, coupling. Can you provide any other examples, yeah, maybe outside your world where this muscle3 can be useful?
You mean, Marcin, apart from macro and micro modeling?
Yeah.
Or other example other than diffusion reaction?
Yeah, exactly. So something from some other, yeah, examples apart this micro and micro model. Have you used this muscle3 in other use cases?
We only used it for South Sudan simulation, but I sent an email to Lawrence and asked him exactly the same question you wanted. He said that we didn't use that for other types of problems.
Ah, okay.
Well, it's not entirely the case. Muscle is being used for blood flow modeling, for instance. But the tool has been released quite recently, and so there are a range of applications that are now basically trying to integrate with the tool. I think the current ones are basically the example that's in the tutorial. With FLE, we have a very basic version. With blood flow modeling, there's a version that is working but not shared yet. And then I believe with Fusion, they're also trying to make an application with muscle.
Yes. And the fourth version of muscle is on the way, and they are working on it. And they are going to get rid of issues and problems of muscle3.
Mm-hmm. And yeah, I'm just trying to imagine in what other cases, yeah, it can be useful for other purposes, and how basically we can use it. But because okay, you are in your world, yeah, this South Sudan simulation and micro models of the migration, but that's fine. But okay, but for this blood flood, yeah, it is correct.
Yeah, it's arterial simulation, so it's blood
arterial
flow.
simulation. Ah, okay, yeah. Okay. Yeah. But how exactly it is utilized there?
I think, Marcin, theoretically, if you have something like muscle3 that connects different submodels, and regardless of timestamps they have, because as I told you, in South Sudan simulation, our time step between macro and macro are the same. But in other problems and issues, we might have different time steps for macro and micro models. And having something like MUSCLE3 that can connect these together and able these submodels to pass messages between each other, I think that's a great potential to use in many issues and problems.
Yeah, so that's one thing, but just to expand on that a little bit. So the predecessor of MUSCLE3 was functionally quite similar, just implemented in a different language, MUSCLE2, and that has been used for quite a wide range of applications. I think MUSCLE3 is interesting if you have models that need to run at the same time at a certain point, and if the coupling is not super straightforward. So for example, you may have two codes that have different time steps, like Alireza mentioned, but they do have to synchronize and run at the same time. Then I think it works particularly well. The other thing that MUSCLE3 has working at the moment already in preliminary fashion and will be better over the coming months is to propagate uncertainty over these coupling links. And that's quite a unique feature that you won't find in many other tools at all. So the idea is you could have a cyclically coupled application, and then you can propagate uncertainty in your coupling between the models. So that's quite an advanced feature that MUSCLE has that I'm not aware of any other tool has. And in terms of the coupling itself, the models don't have to run at the same time. They can also run in an alternating fashion, or you can have combinations of these. And that's basically where the formal framework really begins to shine, because you can define this in quite a straightforward way with the toolkit using this MMSL language.
Yeah, are there any, I don't know, fundamental prerequisites that must be made? Okay, in that we can say, okay, in this situation we can use the MUSCLE3, and in other cases it is not feasible.
So in my opinion, if normal file-based workflow coupling works well, then there's no need to adopt MUSCLE3, because it does have much more overhead than just normal workflow file-based coupling like we do with FabSim3. So that's the first thing. The second thing is that MUSCLE3 does need to run on the target machine. And it's, whereas FabSim3 runs on the user space on the local machine, MUSCLE3 actually needs to have a manager that orchestrates the module, so it needs to be installed on the remote machine. Now, as far as I know, it's working on the Eagle supercomputer, but it did take a bit of effort to get it working there. So that is another constraint that we should be mindful of. But aside from that, it is generic software, and it has a range of very nice features.
Yes, to confirm, Derek, I tried to install MUSCLE3 on Eagle and try to do some tests. I couldn't do that.
Yeah, so I believe people have made it working, but it's not straightforward. And the reason for that is that it has quite specific version requirements for Python libraries, and it's quite clear that it wasn't developed on a supercomputer. So there are some deployment difficulties there. So I think if we want to use MUSCLE3 on a certain supercomputer, we do have to collectively look into that, how we get it deployed. Just to be clear, the issue is not that the tool is huge, very large or something. It's just that it's quite picky with the kind of versions that it needs to have.
I say, if this is crucial, to make it running on Eagle, so Ali, if you can, contact me, so maybe we can just follow it up with our admins,
Absolutely. Thank you much. I noted.
All right, are there any other questions?
I guess not.
Okay, well, Alireza, I guess you finished a little bit ahead of schedule there.
Yeah, because of that message you said to me.
So, well, thanks. First of all, I really want to thank especially Hamid and Alireza for preparing this this workshop, as well as Lorenzo and Dinesh for helping setting up the infrastructure around it. I also want to thank Diana for helping to organize things and correct things also during the workshop. I think overall, approximately 10 to 12 people joined for this workshop, which is, to be honest, roughly the number that I expected. I hope this has given a good insight for everyone about the technical aspects of these two tools, what their added values are, and how you can basically use them in practice. Both within the Hidalgo and the Vecma project, we're happy to provide support for both the tools to help people use them and use them in a way that's beneficial for their research or their engineering. In addition to that, I also want to thank everyone else for attending this workshop. And again, if you have any questions, comments, or thoughts, please let us know via email. There is one last thing that I would like to mention, and Alireza, perhaps you can put that on the screen, but I believe there's a link to a survey that we would like the users to fill in, right?
Yes, yes. I will send that survey to the participants via email.
Okay, so basically after this workshop, you will receive a survey. And yeah, we kindly ask you if you could fill it in. It's just 5 questions, and it's mainly for the dissemination report. Yeah, to fill that. So again, thank you very much.